All right. So once again, for those who don't know me, my name is Clement. I am a final year PhD mathematics student at Cardiff University in the UK. And my PhD is basically about mathematical modeling of biological systems and infectious diseases. All right, so today I'm honored to elaborate or to teach us something about quantitative analysis for research. So without wasting time, I'll just share my screen. And all right. Okay, so we just go straight and keep in mind the meeting is being recorded and it will be uploaded on YouTube as well. All right, so this will be the outline of my presentation. So the first thing I'm going to talk about is I'm going to just give a brief introduction to statistics and statistical methods. And sometimes people ask, what's statistics all about, and what are some of the statistical methods out there? We'll also talk a little bit about types of data variables. And please, can we all mute our audio just because of some feedback? All right, so the next one is type of data variables, and then we'll also talk about steps for dealing with questionnaire data. In most instances, people use questionnaire kind of data, and they don't know how to really go about these things. So yeah, we just give a little bit of hint about that. And the next one, we are going to talk about different data structures. Can we please mute our audios? Let me see.
Maybe
Clement,
yeah.
Give me the host, and I can control that.
All right, so let me
John, can you mute your microphone, please?
Your host now.
Okay.
Okay, so let's try and mute because there's this kind of interactions. All right, so let me just. All right, so yeah, so the next thing is about data structure of quantitative studies, and we realize that, or we learn at the end of the day that the kind or the nature of the data or the structure of the data also informs the kind of statistical analysis you can actually do. And then we talk a bit about some univariate and multivariate statistical tests, and we'll introduce a little bit something about regression analysis and variable selection. And we talk about statistical softwares that you can actually use for data analysis. And at the end of the day, I was also introduce some personal initiatives that I have already started on advanced data analysis, which you can learn for free. And then the last session will be questions and answers, and I hope you will enjoy it. All right, so without wasting time, first of all, what is statistics? So when you talk about statistics, just see it as a science that basically deals with collection of data. And after collecting data, the next thing we do is to analyze the data and then interpret. Interpreting means that based on that analysis, you are going to get some findings. You should be able to interpret those findings and make meaningful conclusions. So that is basically what statistics is all about. There are strictly two types of statistics. In essence, if we are doing any statistical analysis, we expect to see these two areas in there. So the first thing is statistics can broadly be grouped into descriptive statistics and inferential statistics. Now, when you talk about descriptive statistics, it's basically trying to summarize your data using some summary measures and some plots. And keep in mind that at the descriptive stage, you cannot make any vivid or meaningful conclusions. So in essence, when you talk about some of the descriptive statistics, we are talking about these central tendencies like the mean, median, mode, or percentages and so on, just to summarize your data. The measure of dispersion, we are talking about, let's say, standard deviation based on the kind of variables you are dealing with, and then we even have coefficient of variation and so on and so forth. But when it comes to the descriptive plot, we are talking about situations where you use pie charts, histograms, stack bar charts, even scatter plots and so on and so forth. We even have lots of different plots. We have the pirates plot and so on and so forth. And we use these things to just give us a fair idea, some of the patterns that might exist in the data. Now, keep in mind that at the descriptive state, you cannot just get, let's say, a percentage between males and females with respect to, let's say, vaccine intake, and just conclude that And because the percentage of females based on the data where is actually higher than that of males, we can conclude that females are more likely to take vaccines or not. Okay, so keep in mind, at the descriptive stage, you cannot make any vivid or meaningful conclusion. It only gives us a fair idea or a good guess of what patterns and actually summarize the kind of data we are dealing with. All right, so the next stage, which is called the inferential statistics, is basically at that stage where you can now make vivid conclusions. So keep in mind, if you are doing any statistical analysis, we expect to see these two fields of statistics in place. So you do some descriptive summaries, and then the next thing is now start with the inferential statistics. Now, when I talk about the inferential statistics, is basically please let's try and mute our audios. It's basically about statistical tests and statistical models. Sometimes people confuse the two. What is statistical test and what are statistical models? Don't forget, this meeting is being recorded and everything will be uploaded on YouTube. So you can actually make notes as you want, but you would also have the video for yourself to watch at your own pace. All right. So when you talk about statistical tests, keep in mind that there's something we call hypothesis or statistical hypothesis. Now, with the hypothesis, they are basically certain statements that you wish to investigate its validity. Now we have the null hypothesis and we have the alternative hypothesis. The null hypothesis is always what you are seeking to achieve. So here, be careful. There are instances, let's say you are interested in, let's say, let me get an hypothesis. So you want to say maybe one's sex can influence their vaccine intake, for instance. Now, instead of saying that maybe males are more likely or males are more likely to maybe take vaccines than females, okay? Let's say this is an hypothesis you want to investigate. Now, one thing I want you to notice that always your hypothesis in your research should reflect the null. So instead of saying that there's exists maybe significant difference in terms of intake, rate of intake of vaccine between the two sexes, you should rather say there's no significant difference, because that is the null hypothesis. So always make sure when you're writing your hypothesis in your research, you rather write the null, even though the alternative basically is what you might wish it holds. But keep in mind that the null is always what you should write, because once the null is false, automatically the alternative is true. So I just want you to note that always you should write your research hypothesis to reflect the null hypothesis. Okay, fine. So, and then the null is assumed to be true until proven otherwise. Anyway, so statistical test basically seeks to achieve the validities of some hypothesis. Okay, and we have different statistical tests, and then most of the times you are testing about some parameters, okay, just to see whether there's significant difference. It could be checking whether there's significant difference in the means of some variables, or checking whether there's significant difference in the proportions, and so on and so forth. And then now when you talk about statistical models, keep in mind, so the statistical tests, okay, are basically testing the validity of an hypothesis. Now, when you talk about statistical models, it's all about trying to estimate some parameters. So at the hypothesis testing stage, we don't estimate any parameters. We are basically just testing some hypothesis. Now, with the statistical models, what we are doing is that we are actually making predictions, okay? And then in making prediction, we need to estimate some underlying parameters. However, to determine whether those parameters are also significant or not, okay, we need to also use statistical tests in there. So keep in mind that models actually cannot go, they actually go in hand with the statistical test. So basically, until you fit a statistical, until you conduct a statistical test or you fit a statistical model, you cannot make any vivid conclusion. For instance, if I wanted to be able to conclude that males are more likely to, let's say, take vaccine or not, probably, let's say, I fitted, let's say, a model called, let's say, logistic regression. I don't want you to understand that for now. And then I estimated something called odds ratio. It is after I get odds ratio that I'm able to, based on the odds ratio, to conclude that maybe males are 2 times more likely to take the vaccine compared to females or not. Until I fit such a model, I cannot make conclusion based on just mere percentages. So that's the take-home message I want you to get. So at the descriptive stage, you are always summarizing the data, telling us some patterns and giving us a fair idea about some summary measures, but you cannot make any conclusion at the descriptive stage. It is only at the inferential stage where you can now make such vivid conclusion. All right. So what are the sources of data? Data, we have 2 sources of data. We have primary data, and then we have secondary data. Now, when you talk about the primary data, It is situations where the researcher does not have the data at hand or in hand, and they now have to what? Collect the data directly from some main sources, whether through interviews, experiment, or survey, and so on and so forth. Now, when we talk about secondary data, this is situations where you have a pre-existing data. The data is already available from different sources, or maybe from already collected, that you don't need to collect, and it's already available for you to just use. And that is what we call secondary data. So secondary data are basically pre-existing data set that you can actually use for your research, whereas primary data are basically data sets that you now have to collect directly from some main sources through interviews, experiments, and so on. Fine. Now, so that's just a fair idea. So at the end of the day, because we don't have much time, we are only going to expose you to the relevant things you need, and you can actually now expand upon the knowledge by investigating further. So these are just preliminaries. And at the end of the day, when I talk about my other initiatives, it will also be of benefit to most of you. All right. So with the statistical methods for research, one thing you have to keep in mind is that when you're doing any research, at the methodology session, they expect you to emphatically state the kind of statistical methods you are going to use, or the kind of statistical analysis you're going to do, whether you're going to be working with strictly qualitative methods or strictly quantitative methods, or a combination of the two. So the mixed methods is basically a combination of the two. Now, the focus for this presentation is basically about quantitative methods, but I'll give a little touch about qualitative methods. So keep in mind, when you talk about qualitative methods, okay, it's basically situations where you actually collect data based on, and the data we are talking about here in this case is not numerical. So it's data that you obtain through observation, or maybe through some textual or visual analysis, maybe from books or videos, or you did some interviews. Or by interviews, I mean you either did it individually or considered a focus group. So focus group is basically you consider some group of individuals to brainstorm about a research topic, and then as they are brainstorming, then you start making notes about the key findings that were popping up. Please let's try and mute our audios. All right, so that is basically what qualitative methods are about. So the data obtained from the qualitative methods are basically non-numerical. They are not numerical, okay? And keep in mind, how do we analyze such qualitative methods? We have something called thematic analysis and data transcription, and these are basically employed for qualitative analysis. I wouldn't go much into that, but you can do further investigation into it if you really want to do any form of qualitative study. And the next one is the quantitative methods, which is what I'm going to really focus on. And that is where we now do some numerical analysis of the data, maybe through polls, questionnaires, and surveys, and even using pre-existing statistical data. So keep in mind that for quantitative methods, you can actually collect the data from scratch using questionnaires and doing some surveys and so on, or you can make use of a secondary data if it is only available. But there are most instances where the mixed methods becomes very appropriate. There are certain studies where you also need to know, apart from having a data, because we know the focus of everything is that we want to learn from the data, because the statistician believes that once I'm given a data, there are so many hidden dynamics that I can actually investigate and actually uncover about maybe a process you don't even really understand. Okay, so data is very powerful, and that's why without data you cannot make even decisions in the first place. So when we talk about the mixed methods, there are situations where even though the data, you can learn more from the data, you believe that you can also investigate more from your participants. So in such situations, then it will make sense to also consider qualitative study and qualitative methods by using these interviews and then some focus groups or whatever appropriate, depending on maybe your cost or your funding or your budget and maybe the time frame of your research. And so keep in mind that. So the mixed methods are sometimes suitable in most instances, but those of us in the quantitative fields of research, we mostly go for the quantitative methods. All right. So keep in mind, in some PhD studies, you might want to use a mixture, especially when your study participants are human participants, and you believe that there are extra information that the data might not be able to tell you, and that you need to do further interviews to get such information. So keep that in mind. All right. So before we actually start the statistical methods and everything, I mean the quantitative styles, So keep in mind, preceding slides are going to focus strictly on the quantitative bit of research. The qualitative and the mixed method was just a little exposure. Now, before we understand these things, we have to understand the type of variables. What are variables in the first place? So just look at the name. The name is variable. So we could say we actually obtain it from the word vary. So variable is any characteristics that actually varies from one individual or item to the other. So age is a variable. Why? Because age changes from one individual to the other. Height is a variable because it changes from one individual to the other. So just keep in mind any characteristics that actually changes from one individual to the other or one item to the other is basically a variable. Now, all variables can be classified strictly into two. We have quantitative variables and we have qualitative variables, okay? We have quantitative variables and qualitative variables. The easiest way to distinguish these two is that the quantitative variables are variables that are numerical in nature, whereas the qualitative variables, can we please mute our audios? Whereas the qualitative variables are variables that are non-numerical in nature, okay? So just, that's the easiest distinction. So for instance, if I ask you, is age quantitative variable or qualitative? Ask yourself, if I ask you your age, are you going to give me a name or you're going to give me a number? So if I ask your age, you tell me maybe you are 25. That is a number. That makes it quantitative variable. If I ask what is your name, you give me a name, which is a string, which is a factor. If I tell you what is your color, you are not going to give me a number. So that is the easiest way you can distinguish between quantitative and qualitative variables. Now, even within qualitative variables, we have two categories, okay? We have the nominal and then we have the ordinal in terms of their scales of measurement. What do I mean by the ordinal? So you realize that if I ask you about branding of, let's say, or let me use educational level. Now, educational level is not quantitative, right? Because if I ask you your educational level, you might tell me, oh, you have secondary level education, tertiary level, or maybe basic level. And that is, you are giving me a name, isn't it? It's not a number, so it's not numerical. So at least we all can convince ourselves it's qualitative. Now, you can also see that there's a bit of ordering in that. That is to say that when you tell me basic level, tertiary level, and let's say basic level, secondary level, tertiary level, even though they are names, you can clearly see there's this form of ordering in there, and that is what actually gave rise to the type ordinal variables or ordinal scale. So when you talk about ordinal scale, they are basically names, okay, but they are names that has some form of ordering in there. So if, for instance, if I give you a variable like countries, now countries as it stands, if I tell what type of qualitative variable is a country, is it under the ordinal or nominal? You ask yourself, does countries have any form of ordering? As it stands, there's no form of ordering unless you say maybe you are looking at the area or the size of countries. Then in that case, you can now have some form of ordering in there about which country is bigger and smaller and so on and so forth. But as it stands, country, color, they are all nominal. But the very moment that particular variable has some form of ordering, it becomes ordinal. But the whole take-home message is that once a variable is naturally not numerical, it's qualitative. And that's the most important thing I want you to keep in mind. For the quantitative too, we have the interval and the ratio. You don't really have to understand more of the details about what the interval and the ratio does, but just keep in mind that any variable that is numerical in nature is quantitative. That's the take-home message. So I wouldn't waste much time about this. I've already covered these on my YouTube channel, so I'll point you to the other link and you can follow because we don't have much time. All right, so just keep in mind that the nature of the variables also informs the kind of statistical analysis you can do with them. So just keep that in mind. All right. Now, the next stage is about situations where you don't have a secondary data, meaning that the data is not already available. You are using a questionnaire to collect the data. Now, when you collect data with questionnaires, some people might not know what a questionnaire is. This is just a picture, just a fair idea of what questionnaires are. Now, so meaning that we have some questions asking about a particular area, and then we have some responses, okay, where individuals decide. So SD here means strongly disagree. So for instance, do you buy a product which is endorsed by a celebrity? And then we have strongly disagree, disagree, neutral, strongly agree, and then and agree and so on. Fine. So this is the kind of, what we mean by a questionnaire. Now, keep in mind, every question on a questionnaire is called an item. So these are some terminologies. So when you talk about items, so when I talk about questionnaire items or items of a questionnaire, I basically mean the questions. So it's just a technical term. It's nothing much. All right. So
a
now,
quick question.
Is anyone?
Quick question.
Okay. Okay.
The Likert scale you just mentioned.
Okay.
Is that quantitative or qualitative?
All right. So basically, keep in mind that, for instance, if I say, do you buy a product which is endorsed by a celebrity? At the end of the day, you are you are going to choose whether you go which option, whatever you go. But keep in mind, when you are using a statistical software, you are going to use something called dummy coding, and that's basically why I added dummy coding as also part of the heading. So the dummy coding means that you are going to assign numbers. So for instance, if someone chooses strongly disagree, you can call it the person, you can assign one, the next one, 2, 3, 4, 5. Dummy coding means that you can use any numbers. You can even use 31, 32, 33, whatever you want. Just that in the software, you tell them that 31 means strongly disagree. If you use 1, 2, 3, 4, 5, you just say 1 means strongly disagree, 2 means disagree. Now, one thing you have to notice that assigning numbers or dummy codes to such items or such categorical variables does not make them numerical. So let's get that very well. So keep in mind, assigning numbers like, for instance, this one says that strongly disagree means 1, disagree means 2, and so on and so forth. Now, keep in mind that assigning these numbers does not mean, the reason is because I can choose any number to represent strongly disagree. I could have chosen even 3. I could have even started from 0 to 4, okay? But you realize that for numerical variables, if someone is 25, you cannot change it. The person is 25, okay? So keep in mind, assigning numbers to categorical variables does not make them what? Numerical. It just makes them easy for us to make analysis with them. So keep in mind. I hope that answers your question. And there will be a whole question and answer session at the end of my presentation. So maybe if you have any questions, just try and note it down, and then you can ask me every question after the presentation. I hope we are okay. All right. So basically that's that. So now the next thing is that there are instances where you have certain variables that you want to actually quantify. And such variables, they are very difficult to actually obtain or to measure in reality. We call such variables latent variables. So imagine there are instances where you are looking at, let's say, the effect of, let me just use this as an example, effect of supply chain collaboration, collaborative advantage. I don't want you to know what it implies. I just want you to get a certain picture, then I'll explain in details. So for instance, let's say you want to look at the effect of supply chain collaboration, collaborative advantage on, and let's say firm size on, let's say firm performance. When you talk about firm performance, okay, it's something that you cannot naturally just use a simple measure to just quantify the performance of a firm. So in such instances, since these variables are very difficult to measure directly, we call these variables what? Latent variables. Now, for these variables too, it will have subdomains. In essence, if I'm talking about, let's say, satisfaction, if I want to look at maybe factors influencing patient satisfaction, okay, a bit of noise. If I'm looking at factors influencing, let's say, patient satisfaction, satisfaction is a variable that you cannot naturally just measure. However, if I'm talking about satisfaction, or I want to explore the overall satisfaction, I have to look at, first of all, what area of satisfaction are we looking at? If it's, let's say, satisfaction with respect to, let's say, some health services, I have to first of all look at what is their satisfaction with respect to, let's say, in terms of at the reception, what was their level of satisfaction in there? What was their level of satisfaction with treatment? What was their satisfaction with different domains? Now, the different domains that cumulatively would inform their overall satisfaction are what we call the construct. So, for instance, supply chain collaboration, I've given some subdomains. These subdomains imply that they are all important in cumulatively what quantifying supply chain collaboration. Now these ones you can call them constructs depending on your field, and then this variable that I cannot measure directly, but I can only measure them indirectly through these variables are basically what we call latent variables. Fine. Now one thing I wanted you to note is that these variables, we have certain things we call a scale to quantify them, and these scales are nothing but just a normal questionnaire. All right, so keep in mind that suppose you want to look at factors influencing patients' happiness. We have happiness scale. We have a scale to quantify people's happiness, okay? Just that it will take into account different subdomains, and then you now cumulatively get something we call a composite score, which represents the overall score based on all the subdomains to quantify that particular latent variable. Anyway, now one thing I want you to note is that if you use a standardized scale is a scale that has already been developed by people or by experts, has been tested to quantify some of these variables. Fine. Apart from standardized scale, unstandardized scales are just, or unstandardized questionnaires. When I talk about scale, I mean questionnaires. Unstandardized questionnaires are basically questionnaires you develop yourself, and then it has not been tested yet. Now, if you use a questionnaire, keep in mind whether standardized or unstandardized, the first thing you have to do is to check something called reliability or the internal consistency of the responses of the questionnaires items, okay? And why do we do this? Now, so for instance, if you look at this question, they says, do you buy a product which is endorsed by a celebrity? And maybe the person gave their response, I mean, a particular response. And then the next question you ask, do you get attracted to buy products endorsed by a celebrity? So it's more likely that depending on the person's response for the first item, it might influence their response for the second item if the first and second item are related to each other. But there are instances you give a questionnaire to your participant and they don't really read the questions, okay? Some, they just, because they don't have time, they just take it anyhow. And at the end of the day, you realize that internally, their responses are not consistent. So there's something we call Cronbach alpha reliability coefficient, or you can just say reliability analysis. So it's just a coefficient, okay? It's just a single number that is bounded between 0 and 1, such that the closer the number to 1, it implies the highly internally consistent the responses were. And then the closer it is towards 0, then it implies it is weakly consistent. Now, keep in mind that you expect to achieve a high internal consistency in order to be able to be confident with the kind of responses you are going to make use of in your analysis. So keep in mind, that's first thing you need to do. So just don't collect the data. And when you're doing this internal reliability checks, you don't need to include sex, those demographic information. If it's a scale, for instance, something quantifying firm performance, you want to be able to check the internal consistency based on the scale for quantifying firm performance. So keep in mind that if you use a questionnaire, you should always check the reliability by doing a Cronbach alpha reliability. These things, you don't have to do it manually. We have every software, almost every statistical software can do that. And I'll point you to those softwares you can use it for. All right. So the next thing, as I already talked about, latent variables. So keep in mind, it's not only latent variable. There are instances you are just doing using a questionnaire to do any study, which you don't necessarily have to quantify some variables whatsoever. But however, every study you are doing, you should be able to quantify exactly the kind of variables you want to explore. Okay, quantifying means that you can even get a simple item which you believe quantifies that variable, or a scale, a whole scale with some construct, with some subdomains that collectively quantify these. Now, in quantifying such latent variables like what I've already mentioned, for instance, maybe satisfaction, you want to quantify an individual's level of satisfaction with, let's say, school. If I want to quantify your school satisfaction, I probably have to look at some services, your satisfaction with some services of the school, maybe teaching, maybe research satisfaction, different areas. Those different areas is basically what I'm terming as construct. And then the overall academic satisfaction is what I'm talking about as latent variable. Now, there's something you have to do now. So for instance, these constructs would also have some items under it. So information sharing, there will be some items. If I say items, I think by now you should know. I'm talking about the questions in a questionnaire. Now, those items, okay, I mean, so meaning for information sharing, for instance, there will be, let's say, maybe, for instance, maybe 15 items that is trying to represent information sharing. Now, not all the 15 items, even though you actually had maybe a standardized questionnaire somewhere which said it was 15, or you adopted it and added something, keep in mind, even if it's a standardized questionnaire which has already been developed by other researchers, you can always tweak it a bit if you want to seal the kind of things you are doing. Now, what I'm trying to imply is that suppose there are 14 items talking about trying to measure information sharing. Not all 14 items might be useful based on the responses you've gotten, okay? So in essence, we do something called correspondence analysis. Other studies, other statistical fields will call it factor analysis, or you can just combine, just call it correspondence factor analysis to make your life easier. And what this does is that it helps us to identify which items, okay, I mean, items trying to measure a variable, which of those items are highly correlated or highly useful with respect to measuring that variable. So meaning that not all items might be useful in measuring, let's say, a particular construct. So in such instances, the corresponding factor analysis help us to identify which items we should include in quantifying a particular variable and which ones we should take out, okay? So I wouldn't go much into the details. I mean, you can investigate further about that, or you can ask me questions afterwards. Anyway, so that is something you have to keep in mind. This factor analysis is strictly for data that are categorical. We also have its counterpart called principal component analysis. I didn't want to mention that here. And the principal component analysis is basically doing the same thing as the factor analysis is doing. But what is it? And the purpose for principal component, or PCA, is strictly for numerical data. So this is for data which is a factor or categorical, okay? But for numerical data, we use principal component analysis. And the usefulness of principal component analysis is when you have a numerical data, okay, maybe you have a variable called sex or educational level, which you've actually assigned one for male, 2 for females. I told you when you are doing the analysis, you have to assign some dummy codes. You assign some numbers to that. By assigning numbers to the categorical variables does not make them what? Does not make them what? Quantitative. Just keep that in mind. Keep that in mind. And always keep in mind that you can always convert a quantitative or a numerical variable into categorical. Okay, so for instance, age, you can actually recategorize age into less than 18, between 18 to maybe 50 and greater than 50. So you can convert a numerical variable into categorical, okay, but assigning a number to a categorical variable does not make it numerical. So in essence, I would say that you can convert a numerical to categorical, but you cannot convert a categorical to numerical, even though you've assigned some numbers to it. So just get that, or keep that, fine. So there are instances where, so keep in mind, you do the internal consistency and using the Cronbach alpha reliability coefficient, which is just a single number. And then the next thing is you do some corresponding analysis, especially if you want to now investigate whether you need to consider all the items in quantifying some variables, or you need to eliminate some specific items. How many items are you going to eliminate? The principal component analysis, or in the case of factor variables, the corresponding analysis will help you to identify how many variables you should take out using something called script plot. I won't go into that. And then it also tells you which ones are contributing more to quantifying that variable. And then we call those level of contribution communality. So the communality basically tells the amount of variance each of the variables are actually explaining. And so, yeah, you can investigate further about that. So this is just to give you hints and certain things you can actually do right. Okay. Now, there are instances where you want to look at, let's say, the effect or the relationship between let's say the effect of supply chain collaborative advantage, and let's say the size of firm on, let's say, firm performance. You want to do this investigation. But keep in mind, there are also instances where there might exist some form of relationship among your independent variables. So is someone trying to ask? Okay, fine. So we have something called dependent variable. So the dependent variable is the variable you are interested in, okay, or the outcome that you are interested in. And the independent variables are the variables you are not very interested in it, but you want to see how they affect the dependent. Now, what I'm saying is that there are instances where some of the independent variables might be related with each other, okay? And there are instances where your goal is not to explore such interdependency existing among the independent variables. If your goal is to just investigate their effect on the dependent only, then you have to make sure situations where some of the independent are highly correlated, you eliminate such variables that are causing such highly correlation. It introduces something called multicollinearity, which is not something we want to actually obtain in our research. I'll tell you later the effect of multicollinearity. But one thing I want you to notice that there are instances you are also interested in checking whether some variables, even though maybe supply chain might not have a direct impact on firm performance, it could have an impact on firm performance through some variables. So for instance, this collaborative advantage, as you are seeing, is now serving as something called a moderating variable. And we could also have a mediator, okay? So for instance, collaborative advantage is like mediating the relationship between supply chain and firm performance, and firm size in this case is trying to moderate. Moderate means that its presence can either increase or decrease the relationship between the variables. Fine. There are instances you want to explore these kind of complexity in terms of the relationship. What do? You can either use something called hierarchical regression or something which is very powerful called structural equation models, okay? So you can actually use that to explore such complex relationships that exist between the dependent and some of your independent variables. Strictly situations where you have latent variables and then the latent variables are being quantified based on some construct, then you can actually investigate such complexity, because it's very important to identify if there could be some variables that are mediating or also moderating. So I wouldn't go much into that. So let's continue. So basically what I was talking about here was strictly when you had a questionnaire and the questionnaire data and you wanted to do further exploration. But let's consider situations where you have a secondary data. So you have a secondary data which is strictly numerical, and then we have some bit of categorical. So for instance, female here is just representing sex, and then 1 means a female and 0 means a male. Anyway, so keep in mind, in this case, you realize that we've assigned a number to the variable called female, or in this case, sex. But it doesn't make it what numerical. Anyway, we assign numbers for the software to be able to do such analysis with them, and the kind of models you might want to use as well. Okay, now for numerical data, one thing you have to keep in mind. So now I am still I'm not considering categorical variables as numerical, but because we've quantified them with numbers, I just want to use the term numerical data. Now, for numerical data, we have different structures. Now, one thing you have to notice that the type of variable tells the kind of analysis you want to do, and also the structure of the data. So keep in mind that the data might have the same variables, okay? However, the way it was collected and its structure can also inform completely the kind of statistical analysis you can do on them. So now there are different types of data. I'll just different structures. I'll just explain just a few, or the most important structures that we see in our daily lives. The most predominant one is technically the cross-sectional data. So what is a cross-sectional data? So one take-home message is that for cross-sectional data, you are collecting data on more than one variable. So for instance, we have data on wage, data on education. I mean, I don't know what this variable was representing, right? So we have data on wage, maybe education, whatever, experiment, whatever, and maybe gender. So you see, you collected several variables, but you did that within one time point. So here we collected this data within a year, and technically we consider within 1990. So you realize that for cross-sectional data situation, let's say you say for 2021, I want to collect data on individuals, maybe let's say vaccine intake. I want to collect data on their sex, their educational level, maybe where they stay, maybe whether they've taken a first dose or not, whatever. So and then maybe I'm collecting that data for the year 2020. It doesn't matter the time frame you collected individual. Let's say I'm calling the individuals as individual 1, 2, 3. It doesn't matter whether you collected. It doesn't mean you have to basically collect the data of all your individuals, let's say the same day. but the focus is your time frame. Your time frame is that you want to collect the data for a year or within a year. Now, keep in mind that for cross-sectional data, each row corresponds to a single individual, okay? And then the individual is only studied, or information is collected about the individual just once within that one time point. So here, suppose we have 100 individuals. I collected information about their wage, medicational, whatever, SPA, I don't know what the variable was, and female, let's say, which is representing sex. I collected this information, but you realize that I did it within a year, several information within a one time point. And that is why we call cross-sectional data. Cross-sectional data implies that if you want to do some specific analysis, maybe you want to look at the effect of this SPA and their sex on their wage. In that case, you can only use some statistical models or tests that is strictly for what cross-sectional data. So keep that in mind. And the next one is something called pooled cross-sectional. So keep in mind, once it's cross-sectional, it implies that for each individual, we collected their information just once, but several information just once. Now for the pool, there are instances where maybe within the year 2000, you collected information on 100 different, let's say, the individuals could be humans, it could be houses, it could be companies, it could be anything, okay? So for instance, let's say this one, they were collecting information about households, okay? Now, so for the first 100 households, they collected their information within the year 2000, but they realized that they still needed to collect extra data. So they also considered other different households for another year, okay? But keep in mind, the goal is that for each household, the data was collected once, okay? But situations where the data is collected once, but we also considered individuals in different time frames, that makes it what we call a pooled cross-sectional. So keep that in mind, all right? So whether pooled or not, it's still cross-sectional because we collect information about individuals once. Now we have and this particular third data structure is mostly very seen most of the time, but most people don't know how to go about them. We call them longitudinal data, so or also called panel data. What are panel data or longitudinal data? As the name goes, longitudinal. So this is situations where you are actually taking measurement for each individuals, not only once, but it could be more than once. Okay, so for instance, you can see them as like a follow-up kind of data, where let's say for individuals or subject one, the information was collected in 2000, and then in 2001 we collected another information from that same individual, and then maybe it could be more than 2 time points. Maybe we did it over a 10-year period, okay? And then we also did the same thing in parallel for subjects 2, and so on and so forth. Such a data is what we call panel data or longitudinal data. If you wanted to do any analysis, you cannot use a model that is strictly for cross-sectional for panel. So keep that in mind. So you can clearly see at this stage, even without being a statistician, that the structure of your data also informs the kind of analysis you can do. Now, and so keep in mind, panel data is basically a combination of what a time series and a cross-sectional. So panel data is a combination of a time series. I'm going to talk about a time series shortly. So time series is basically a data that is collected over time, okay? The data that are collected over time, okay? But for longitudinal data, we are collecting several information. The several information is for each subject is making it cross-sectional. But what we are saying is that you are collecting it at more than 1 time point for each individual. And that makes it what a panel data. All right. So these are some of the structures or the structure of the data you might get. And these kind of data, suppose they are already available by a company or in a hospital or whatever, this is what we call a secondary data. All right. So now the next stage is, how do we do, what are the statistical tests and statistical models and so on and so forth. Now, keep in mind that I told you there's something called some hypothesis. And hypothesis, when you talk about the hypothesis, is basically a statement that you want to investigate its validity. So for instance, males are more likely to die than females, or males have maybe low life expectancy than females, and you want to investigate these things, and then you collected the data and so on and so forth. And then now you want to compare whether the average age of males is significantly different from that of females, and so on and so forth. Now, one thing I want you to note is that research statistical tests seeks to what? Test some hypothesis about some parameters. So it could be you are comparing the means between some groups. The groups could be dependent groups, independent groups. There could be more than one group. There could be 3 or more, and so on and so forth. Okay. And there are instances where you are not only comparing a single variable. Let's say you are comparing several variables, checking whether all those several variables are significantly different between some groups or not. All right. So here I want you to note, what I want you to note is that statistical tests can also be categorized into 2. We have the non-parametric test and we have the parametric test. Now, when you talk about the parametric test, I want you to take note of these very well. Now, the parametric tests are statistical tests that has some strong and specific assumptions that needs to be what? Met. And the non-parametric tests are basically robust to assumptions, and then the assumptions could be weak and not necessarily strong. Anyway, so for the parametric test, they have strong and specific assumptions. What do I mean by strong and specific assumptions? Suppose you want to do a mean comparison. You want to compare whether, let's say, the mean performance of students of, let's say, Cardiff University students is, let's say the mean performance of students is significantly different between, let's say, 3 universities. You want to do that comparison. Now, an example I always use is that, suppose you have, let's say, 2 classes, class A and class B. And for class A, let's say you consider 3 students from class A and you consider 3 students from class B. And for class A, let's say their marks for, let's say, their overall or total score, let's say for class A is, let's say, 5, 10, 20. And let's for the other class, let's say is maybe 1, 2, and let's say 50. You realize that one group has some outlier. An outlier is extremely small or extremely large observation compared to the others. If I want to use a statistical definition, it's any observation or any measure or number that does not fall within 3 standard deviations of the mean. That is like the statistical definition. But I just want you to keep in mind that it's any observation that is extremely large or high or extremely small. So it's not only extremely high. Extremely small too is an outlier. So it's just abnormalities anyway that exist in such instances. Fine. Now, one thing I want you to notice that the mean is affected by outliers. Always you realize that when we have a number that is extremely high and you compute the mean, you see the mean is trying to sum and divide by the number of observations. That's the arithmetic mean. You find out that always the mean it converges towards the highest value. So if you have one particular value that is very high, it inflates the mean. Okay, so in such instances where you have such a very high number, you might get maybe the mean performance or the mean grade of that class to be high than the other class. And you just say that, oh, since the mean score of class B is higher than that of class A, then it implies students in class B are doing better than class A, not knowing that it is only by one student's contribution that inflated the means. So that is what we mean by parametric assumptions. So keep in mind, to do mean test or to compare means between groups, whether strictly 2 independent groups or 2 dependent groups or 3 or more independent or 3 or more dependent. I'll explain what I mean by dependent and independent groups. So in such situations, the first thing you need to check is that, is your data normally distributed? Okay, so normal distribution, basically, if a data is normally distributed, the mean, the median, and the mode are almost equal. It's not always equal, but statistically we say when they are equal. But in practice, I mean, keep in mind, sometimes practice and theory sometimes contradict a little bit, but keep in mind that if I have a data and I find the mean, and let's say the mean is 12, and then I find the median, and the median is, let's say, 11.9, and the mode is, let's say, 11.8, I can say that such a data is almost normal or is almost normally distributed because the means and the median and the mode are almost equal. Okay, but keep in mind, you have to do a statistical test before you can conclude that the data is normally distributed or not. I told you, using means and medians or descriptive summaries, you cannot make conclusions. You can only say that, oh, the data appears to be normal. But if you want to now do a mean, to check whether the data is normally distributed, we have some normality tests we do. Examples are, we do something called Shapiro-Wilk test, which is a parametric normality test. You get access to the recording, so don't try to jot everything down. You get access to the recording. the YouTube video of this at the end of the presentation. Fine. So Shapiro work is a parametric test, which is more useful when you have a sample size at most 5,000 and below. The parametric, the Shapiro work is actually what you need to consider. And then we have instances where you have a very large data set, and let's say more than 5,000, and you still want to check whether that data is normally distributed. Then we have other non-parametric tests like the Kolmogorov-Smirnov test. We have something we call Anderson-Darling test, which are all normality tests you can actually use. We even have skewness ketosis tests. So keep in mind, there are so many tests, even the parametric, the Shapiro test, we even have Shapiro-Francia normality test and all sort of things. Fine. So keep in mind, if you want to do mean comparison, the first thing you need to do is to check whether your data or the variable, the numerical variable you want to compare between the groups, check whether that variable is what normally distributed. If that variable is normally distributed, then you can now use all these parametric tests I'm talking about. If it is not normally distributed, don't kill yourself. It implies that we know the median is not affected by outliers. What do I mean? If I have, let's say, three numbers, 2, 3, 5, okay, and I find the mean, and then I find the median will still be the middle number. If I increase the 5, 2, 3, 5, if I increase the 5 to even 100, the median will still be the middle number, but the mean will change, okay? So that's why we are saying that the mean is affected by outliers. The median is less susceptible to outliers. So situation, and keep in mind that when the data is normally distributed, we said the mean, the median, and the mode are almost equal. So technically comparing the means for when normality is attained is also the same as actually comparing the median. Okay, so these central tendencies, when the data is normally distributed, are basically doing the same thing. And so comparing median is not a wrong thing. Most students just go straight and use the median, the mean tests, and then they don't explore these assumptions. And keep in mind, if we're using a statistical test or a statistical model and it's parametric, don't just use it without testing these assumptions, or else if we're publishing such a study, it can be rejected. So just keep that in mind. Just go by the protocols. These are like statistical protocols you need to go through. Anyway, so when the data is not normally distributed and you want to compare the means, I told you cannot go by the mean comparison if it's not normally distributed. In that case, you can do the median test and it will still give you the kind of conclusions you wanted to infer. And then you can also compare something called proportions and do correlation tests and so on and so forth. Now, for the mean test, keep in mind that suppose you have two dependent groups. What I mean by dependent group is that suppose you want to compare, let's say, the effectiveness of a drug on, let's say, 100 patients, okay? And then you expose the 100 patients to, let's say, some placebo or some control. And then at another instance, you gave them the drug itself, okay? And probably you recorded maybe, let's say, the amount of, let's say, parasites or the number of parasites within. I'm just giving an arbitrary example. So in situations where you consider the same subject, you take some measurement and you consider the same group of individuals and you take their measurement again after the introduction of, let's say, some form of intervention. In such instances, the two data sets are dependent because they are all coming from the same group of subjects. So that is what I mean by dependent groups. So situations where you have dependent measurement or obtained from the same set of individuals, then if you want to and strictly when they are strictly two, then in that case, if you want to do a mean test, suppose the data is already normal, okay? Then in that case, you do something called paired t-test. So the paired t-test is just checking whether there's significant difference in the means of, it could be means of anything, any variable, maybe means performance, mean, whatever, checking whether there's significant difference in the means between strictly two dependent groups. If the groups are independent means that if I consider, let's say, 12 males, and I consider 12 different males, and I take measurement on the first 12 set of males and another measurement on the other set of males. They do not necessarily have to have the same sample size. It could be 12 males and let's say 15 other males. Still in that case, the data that you obtain or the measurement you obtain are independent because the subjects were not the same. So I would have used just males and females, and that would be straightforward. But I just want you to understand that even if it's the same, even if there are two groups of males, since there are two different groups of males, it still makes such measurement what independent. And so when they are strictly two, when you are comparing significant difference in means between those independent groups, then you use something called independent t-test. Now, suppose you have more than two groups, okay, more than two independent groups, then you use something you call what? ANOVA, okay? So ANOVA is just an extension of the independent t-test. Now, for the paired t-test, where we have dependent groups, for instance, you take measurement of some individuals at, let's say, 3 time points, okay? So in that case, if it is strictly 2 time points or 2 instances, I told you, since it's coming from the same set of individuals, that is a paired t-test, okay? If you want to compare the means. Now, when there are more than 2 dependent groups, then use something called repeated measures ANOVA. So the repeated measures ANOVA is also an extension of the paired t-test, whereas the ANOVA is an extension of the independent t-test. Now, keep in mind, after doing ANOVA, where you are looking at a mean comparison between 3 or more groups, after doing that, and then let's say the test comes out that there's significant difference in the means, the next thing you have to do is to check whether there's significant difference pairwisely. The ANOVA would just say, oh, there's significant difference between the means between the 3 groups or more groups, okay? But you now have to compare pairwisely, the first group against the second, the first against the third, and so on and so forth. And that is what we call multiple or pairwise comparison, or multiple comparison, or pairwise comparison. And then we have different methods of pairwise comparison. We have the Chaffee, we have the Tukey, we have the Bonferroni, and so on and so forth. But the Bonferroni is a bit robust. And so keep in mind, after doing ANOVA test, you can further do a pairwise comparison using the Bonferroni and pairwise test and so on. Fine. Now, keep in mind about the pair t-test, the independent t-test, the repeated measures is strictly one variable. The repeated measure is like one variable collected at 3 instances or more from the same group of subjects, right? Now, there are instances where you want to compare maybe the mean score, the mean height, the mean weight across some groups. Someone could have, let's say the groups are 3 or more groups, let's say across, let's say race. So we have, let's say 5 race or something, and they want to check whether there's any significant difference in, let's say, the mean intellect between races. So in such an instance, let's say they are not only interested in just the mean intellect, they're also interested in, let's say, the mean height, the mean weight, and so on and so forth. One could have chosen to use ANOVA for each of the variables and compare between the groups. But when you do it in that case, you lose something you call some degrees of freedom. So keep in mind, or let's say the power of the test is very weak. So keep in mind that doing several tests at the same time is always much more less costly and much more efficient than doing them individually. So doing separate ANOVA, you can actually combine all those variables you wanted to do separate ANOVA for and do something called multivariate ANOVA. So keep in mind, all these univariate tests that I mentioned, we have its corresponding multivariate case where you are not only comparing one you are not only comparing, let's say, considering only one variable and doing a pair t-test. Maybe you are doing a pair t-test based on, let's say, 3 different variables. You can actually do all of them at the same time. Let's say you are doing an independent t-test, and then instead of doing separate independent t-tests by comparing between 2 groups, maybe you have more than one variable you want to really compare between those 2 groups. So instead of doing an independent t-test, you can do its multivariate version called Hotelling t-test or t-square. And that is basically what I mean by whenever multivariate analysis is possible, go for it instead of doing the univariate case. You only go for the univariate case when you're only considering a single variable at that instant. But if you want to measure, and keep in mind for the univariate case too, for instance, the ANOVA, the groups should not necessarily be only one categorical variable. It could be more than one. If it is only one, then we say we have a one-way ANOVA. If you are comparing a single numerical variable across 2 different, let's say, 2 different categorical variables, then we have a 2-way. If there's 3 different categorical variables at the same time, then we have a 3-way ANOVA, and so on and so forth. So I wouldn't go much into the details. Now, I told you all these parametric tests can only be used when the data is normally distributed. If the data is not normally distributed, these are their corresponding non-parametric tests, which test the median. Now, for each of these, you see, if you look at the pair t-test, the first test is the corresponding non-parametric test. So I made it in such a way that For instance, the repeated measures ANOVA, 8 non-parametric test is called the Friedman test. And then let's say MANOVA, which is the multivariate analysis of variance, where you are comparing several numerical variables across 3 or more groups. In that case, the non-parametric version is called multivariate Kruskal-Wallis, okay? And the univariate ANOVA, the non-parametric version is called Kruskal-Wallis test. I have actually written in such a way that depending on the position, the non-parametric version is what is at this session, okay? So keep that in mind. And then you can also test proportions, do correlation analysis, and so on. So these are just a summary of just the few statistical analysis you can do. So keep in mind that the take-home message is that you can actually do univariate test as well as multivariate test, okay? And for any test you do, check whether the data is normally distributed. If it's not normally distributed, then comparing the means will not make sense because it is going to lead to biased results. Because I told you the mean is susceptible to outliers compared to the median, all right? So in such instances where the data is not normally distributed, then you want to test the means, the medians instead, all right? So the next thing is about the models we were talking about. So I told you for the models, it helps us to make predictions, and it also helps us to quantify something called effect sizes to be able, for instance, if I want to know whether males are 2 times more likely to die from, let's say, an infection, it is after I have fitted a model that I can only make such inferences, okay? So keep in mind, fine. Now, if you want to do regression analysis where you are looking at the effect of some independent variables or some regressors on some outcome variable, keep in mind when the data is cross-sectional, I've already explained what cross-sectional data is. If the data is cross-sectional, now one thing you have to notice that when you're using a regression model, the nature of the dependent variable determines, you see, I've already talked about the fact that the nature of the data structure informs the kind of analysis, okay? So you realize that for each bullet, I kind of bring a square bracket of the kind of data you can use for that. Now, one thing I want you to note is that for regression analysis, the nature of the dependent variable, the nature of the dependent, not the independent, the dependent, also informs the kind of regression you can actually do. So if the dependent variable is continuous and you want to fit a regression model looking at the effect of some independent variables on the dependent, you use something called OLS regression. If, let's say, the dependent variable is categorical, the dependent variable, let's say it is, you are looking at maybe survival analysis, and you are trying to look at factors influencing, let's say, the survival of individuals, where for each individual, the individual is either dead or alive. So it means that it is dichotomous or the responses are binary. So whether dead or alive, okay? So in such an instance, if I want to explore the effect of, let's say, some covariate or some independent variables on the status of, or the survival status, then we use something called binomial regression, okay, or binary regression. There are instances where the dependent variable has more than 2 categories, if it is strictly to binomial or binary, but there are instances where it has more than 2 categories. Then we call that, please, can you mute your audios? So situations where the categories are more than 2, then we call it multinomial regression. Now, most people confuse multinomial regression with multivariate regression. Now, keep in mind, in regression setting, when I say a simple regression model, is a model. Please, can we mute, John, can you mute your audio? All right, thank you. So when you talk about a simple regression model, whether it has dependent, as in categorical dependent variable or continuous dependent or a discrete dependent variable, we say a regression model is simple when we have only one independent variable or one predictor variable. But when we have more than one predictor variable or independent variables, then we call it what? Multiple regression model. So keep in mind, when I say a simple regression model, it is a regression model with only one independent variable. When I talk about multiple regression model, it is a regression model with several independent variables. But when I talk about a multivariate regression model, it is a regression model with more than one dependent variable. More than one dependent variable. So it means we can actually have a multivariate simple regression. So if I say a multivariate simple regression, it means that it has more than one dependent variable, but only one independent variable. Then it becomes a multivariate simple regression. And I can have a multivariate multiple regression, where I have multiple dependent variables, but I have several independent variables, and that's what I mean by that. So keep that in mind. Now, if the dependent variable is continuous, you use OLS regression if you want to do a regression. If it is categorical, you use either a binomial if it has two categories. If it has more than two categories, you use a multinomial. There are instances where it is categorical, but there's a bit of ordering in those categories, okay? Like you could see, maybe let's look at maybe the dependent variable is grade of infection. And let's say we have low level, moderate level, and high level. Even though it's categorical, you could see there's a bit of ordering or ranking in there. So in that case, you can use something called ordinal regression anyway. I didn't write it here. And there are instances where the dependent variable is count. If I say count or discrete, what I mean is that there are instances you are looking at factors influencing the number of road accidents, let's say in a country. If I'm looking at factors influencing the number of road accidents, since the number of road accidents is what I am interested in, that's my dependent variable. Now you realize that that variable can only take whole numbers. The number of road accidents can only be, let's say 2, 5, 10, it cannot be 2.5. So that's what I mean by discrete or count. So when a dependent variable is count, you use something called Poisson regression. Even this Poisson regression has some assumptions because all these models are parametric models anyway. So the Poisson regression assumes that the mean of the dependent variable, the conditional mean of the dependent variable is equal to its variance. If that assumption is not met, then you can also use other class of regression model, for instance, other class of count regression or discrete regression model, such as quasi-Poisson or negative binomial regression. So keep in mind, the Poisson regression, quasi-Poisson, negative binomial regression are strictly for count dependent or dependent variable that are strictly continuous, okay? So these are just a few. So, and all these I mentioned is strictly for a cross-sectional data. But there are situations where this same cross-sectional data you've obtained to do what you call the generalized linear model. So keep in mind, all these models belongs to a class or a family of models called generalized linear model. So if you hear GLM, it shouldn't confuse you. It's called generalized linear model. The reason is because all these are predicting the linear effect of the independent on the dependent. That's why it's what is called linear. Anyway, fine. But situations where the cross-sectional data was also now repeated at different time points, meaning that you now have a longitudinal data and you still want to do all these kind of analysis, we have their corresponding models called generalized linear mixed models. So the models that I mentioned here, we call them fixed effect. Fixed effect in the sense that the independent variables are only the variables that, we are considering and looking at how they affect the dependent. But there are instances where you collected this same cross-sectional data over time. The time interval or the time domain is not, you are not interested in the time domain, but you can clearly see that the data is now repeated longitudinally over time. You need to account for that temporal replication. When I say temporal replication, I mean that repetition in time. You need to account for that in your regression model. And that is, and such variables that causes extra variation or variability to the data. Whether it could be variability due to time, we call it temporal pseudo replication, or maybe you considered the measurement in a certain country a number of times, or measurement in some farms a number of times. So in that case, it implies that there's variability due to location, and that is what we mean by spatial pseudo replication or spatial variation. So in essence, any variable that is not of interest to you, that you're not considering them as independent variables. However, because of the nature the data was collected, they introduce extra variations. You can consider them as something called random effects in your model. The fixed effect variables are the independent variables you want to look at how they affect the dependent. And the random effect are variables that you're not really interested in them, but they introduce some extra sources of variability, whether in time, and then whether by spatial in terms of location and even subject and so on and so forth. Fine. So so keep that in mind. So for instance, if you believe that you've collected information, let's say even a cross-sectional data, you collected information about of a cross-sectional data, and you believe that each individual would have different characteristics about, let's say, the dependent. Maybe the dependent is about maybe their satisfaction with something. You can actually add a variable which represents the unique IDs of each respondent and add that as a random effect in your model. In that case, you are trying to tell the model that there's some extra variability due to the subject effect, or due to the fact that each participant will have different variations of variability in the outcome, then you can add like a dummy code to represent such a random effect. Okay, so just keep in mind that mixed models are basically situations where you have other sources of what variation due to time or maybe space, and you want to account for those variables. Meanwhile, you also want to look at the effect of some independent variables on the dependent. Then you use something called generalized linear mixed models, okay? And these are strictly for what? Longitudinal data. What generalized linear mixed models can do, you can also use something called panel regression for them. Okay, so here, panel regression can also be, I should have brought it also here. So panel regression can also be used for generalized linear mixed model. And most studies, you can actually fit the two class of models and compare which one is doing best based on the data anyway. So it's just a research area I'm giving you. Fine. So, and the next one is something called generalized, we'll finish very soon. The next one is something called generalized additive models. And with this one too, we have its fixed effect and its mixed effect. So if I talk of mixed effect, I'm sure by now you understand that we have other variables that are not independent, and they are also introducing other sources of variability, which you want to account for. Fine. Now the additive models, these are things maybe some of you might not be familiar with. So just get the fair idea so that you know which model is very appropriate for the kind of data you have. Now, you see, for the linear models, it's looking at the linear relationship of some independent variables on a dependent. But there are instances where some of your variables do not have a linear effect or a linear relationship with a dependent. Their relationship could be nonlinear. It actually could be curvilinear and so on and so forth. Or their relationship could even be quadratic or cubic in nature. Okay, and you can actually explore that by just doing a scatter plot. And then the kind of patterns that exist will tell you. Anyway, fine. Now, one thing you have to notice that situations where some independent variables do not have a linear relationship with the dependent, and you are still using a linear model, you are doing a wrong thing. You can still use a linear model, but you have to be able to deal with that non-linearity. And that's what the additive models do. So the additive models help us to fit something called splines, okay? Like example, like a B-spline. It helps us to fit something called spline functions to such variables which has a nonlinear relationship for us to be able to smoothen out the nonlinearity so that we can now do a linear prediction. So just keep that in mind, that that's basically what the additive models are doing. So the additive model is just a form of extension of the generalized linear model or generalized linear mixed model, where in this case, we are adding for some independent variables, we are adding or fitting spline functions to them to smoothing out non-linearity in such instances. Okay, so just keep that in mind. And there's also a recently developing methodology that most statisticians even don't know. So most statisticians, most of them don't know about this. We call it functional data analysis, which I just dubbed FDA. So this functional data analysis tool is strictly for longitudinal data. But you realize that there are instances where you have a longitudinal data, but the data you are interested in exploring patterns. Your focus is exploring patterns that exist in the data, but the data was collected longitudinally. Then the functional data analysis is a perfect candidate for that. But what it does is that it converts the data from a different space, from this real space, into something called, I don't want to go into the mathematics, but it converts it to something called Hilbert space. And with that, it now helps the function to be represented in a different in a different space, such that you can even get clear-cut patterns, eliminate noise that exists in the data, and get clear-cut patterns that exist in your data. And keep in mind that all the statistical models we know, we have its corresponding functional version. So it means that ANOVA, we have a functional ANOVA. We have a functional multivariate analysis of variance. So we have a FANOVA there. So just keep in mind. So keep in mind all the statistical models or statistical tests you've heard of, we have their corresponding functional models or functional versions. Okay, so keep that in mind. And it's strictly for situations when you want to explore patterns and you want to also investigate, let's say, the rate of change. So since it's like a continuous function now, the data could be discrete, okay, but it converts it into a continuous domain. And in that case, you can even do differentiation if you want to look at the rate of change and so on and so forth. So, and also as clear-cut patterns, whereas it eliminates some noise and all sort of things. Fine, so keep that in mind. There's also another class of statistical models called machine learning algorithms, and they are literally taking over the classical or the frequentist statistical models. Okay, so the machine learning algorithms, they are, as it says, machine learning. So they are mostly automated, okay, either supervised or unsupervised, and it actually helps to also explore. So all the regression models I've mentioned, we have the machine learning equivalent, like classification trees, where these models, what they do is that they actually fit your regression model and present the output as a structure. And it helps you to be able to explain to non-experts or non-statisticians. And for instance, I wish I could have shown some of my publications or some of these class of models, like the kind of model output it gives. Very nice output, but it gives you the regression model in a form of a structure, a tree structure that helps you to know what is really going on. All right, so keep in mind, we have classification tree, we have random forest, we have gradient boosting machines and all sort of things, and they can actually be explored for both cross-sectional and longitudinal as well. Now, when you're fitting a regression model, there are instances you have several independent variables, but not all of them. You wouldn't want to consider all of them. So for instance, let's say you have a variable called body mass index. You know, body mass index, or your BMI, is actually the ratio of your weight divided by the square of your height. So it's just the weight divided by the height squared. Now, if you have a data with the weight, height, and body mass index as your independent variable, you are going to get a very poor fit, or a poor model. Why? Because the weight, the body mass index, which is an independent variable, is also dependent on two independent variables, which are your weight and your height. Okay, so if you have a regression model which has all these three models, all these three variables in the same regression model, you are going to get something called multicollinearity. When multicollinearity, that's why I said beware of multicollinearity. Multicollinearity is when we have high correlation existing among some of your independent variables. Your goal is that you want to look at the effect or the correlation between the independent variables on the dependent, okay, or the effect of the independent on the dependent. And situations where the independent themselves are highly correlated, you need to be able to deal with that. Okay, if you don't deal with that, it causes something called multicollinearity. And the effect of multicollinearity is that you are going to basically get wrong outcome. So you will see situations where your overall model is significant, but none of your predictors is significant. Technically, the overall model is expected to be significant if at least one of your predictors is significant, okay? But situations where the overall model is significant, but none of the predictors were significant, and vice versa, or situations where the overall model is not significant, but at least one of your predictors is significant, then that is a multicollinearity. And then so multicollinearity actually brings about wrong inferences. Okay, so that's something you need to deal with it. And we have so many ways of identifying multicollinearity. You can compute something called variance inflation factor or tolerance. I wouldn't go into most these details. I'm just trying to expose you to these things, get the knowledge of them, and then when you're doing the kind of regression and all these things, you know which one you need to consider and the kind of information you can actually employ as well. Now, situations when you want to do a regression model, but the independent variables are highly correlated, we have a way of selecting the variables, okay? And so that we have some variable selection techniques. We have something called stepwise regression, or you can use something called penalized regression, okay? And then the penalized regression, we have three distinct types. We have something called the ridge regression, the lasso, and we have something called elastic net, which combines the ridge and lasso. These are ways of identifying which variables you should consider in your regression. And don't forget principal component analysis. I should have also included it here because it can also be used for that. And we also have another class called recursive feature selection. And all this helps you to identify which variables you should consider in your model. All right, so keep that in mind. All right, so now we've talked about, I've just given you a brief introduction about what statistics is about, this kind of statistical test models and the data structure. And the take-home message is that the nature of your dependent variable tells you the kind of regression model you want to do. And also the structure of the data, whether longitudinal, cross-sectional, or time series, also tells you, I didn't talk about time series models, okay, but I've already covered that on my YouTube channel. I will explain that in a jiffy. So just keep in mind that the nature of your data or the structure of your data also informs the kind of analysis. Now, to do statistical analysis, strictly to do quantitative analysis, how do we do it? Do we do it manually? No, we have statistical softwares for that. The basic softwares are, I'm sure you've all heard of Excel. I didn't add Excel here, but keep in mind that in Excel, it has an extension called Excel Stats. And that extension, even though we have some add-ons, but the Excel Stats gives you extra functionalities that helps you to do much more advanced analysis in Excel. And we also have SPSS, which is usually used by the social sciences. If we're a statistician, most of the times, that's the first software they expose us to. But keep in mind, over time, you realize that you are going to stop using it. I'm not saying you should stop using it. For social sciences, that's fine because you use softwares that you are familiar with or that is predominant in your department. And then we have Stata, we have eViews, the Stata, eViews, Minitab, Gretel. They are mostly used by most people into econometrics, basically those who do more of regression, more of time series analysis, and so on and so forth. Now, these class of statistical softwares are not programming softwares. And I should have added MATLAB. Okay, MATLAB is here. So these softwares are not statistical software. I mean, they are not programming softwares, but they are statistical softwares written based on a programming language. Now we have some softwares called programming languages, and one is called R. And we have Python, we have Julia, we have SAS, and we have C++ and MATLAB. Now keep in mind, R and Python are taking over the data science field. So these are strictly programming languages. And the beauty about programming languages are that it gives you extra flexibility to create your own functions, to create, for instance, you are doing a plot, you can decorate or beautify your plot to any degree you want. It's like you have control to do whatever you want. And then you can create your own complex functions, create your own complex models, whatever you want to do, you have that flexibility. Most of these software, I mean, the first list, they are very rigid in terms of their setup. In essence, what I mean is, even though they have some syntax, you can also create certain things, but generally, you can only use what is in there. But for these the programming languages, you have extra advantages over the kind of analysis you really want to do. Now, the take-home message is that go for R if you want to do statistical analysis. R is much more powerful, and I'm going to now talk about my initiative. So basically, I've already started an initiative on advanced data analysis. So it's like doing intensive data analysis using R programming software. And I already have a YouTube channel for this. And I manage the class using a software, a website called Piazza. So Piazza, the advantage of the Piazza is that, and everything is free. So just join and learn for free. So for the Piazza, it implies that all the YouTube channel, the YouTube videos you watch, the packet, the script or the code that I use, the data and everything, including announcement, including all materials that I use, they are uploaded on the Piazza. If I want to send an announcement to students, I also use the same Piazza and send it to all your emails in an automated way. Okay, so the Piazza helps you to be able to have direct access to all my all the learning materials. Okay, so R is taking over. Okay, and the beauty is that now with statistics, ability to do advanced data analysis with the programming language like R, it automatically induces or helps you to improve your employability. All right, because every company works with the data. Okay, so keep in mind, you don't have to only be a statistician to involve yourself in data analysis. Okay, so you can actually be someone in, let's say, education, someone in, let's say, medicine, and you should be able to effectively program and do data analysis. If you're a medical doctor, or let's say you're a lawyer and you can do advanced statistical analysis, and keep in mind that every field they have data. So in the law field, they have a data, you need to analyze this kind of data and all sort of things. They wouldn't go and look for a statistician and pay them huge money. They can employ you and then you get something as well. So, and keep in mind that with these skills, when you're going for job interviews, you don't go there to tell them what they want to hear. You also tell them the kind of things you can offer. And this is one of the things that I say with this, it gives you, it can make you self-employed. And I benefited from this back in Ghana. And then now I want to actually help all other students. So the focus is to improve mathematical programming among students, specifically in Africa, but everyone is also welcome to join and learn for free as well. So keep in mind, so take it serious. Most of the times when things are free, people are not serious with that. And some people watch the YouTube chat, the videos, they download and all sort of things, and they forget to subscribe. Please do subscribe to motivate me as well, and then and share with your contacts as well. So that's basically the end of my presentation. If you have any questions at this stage, I will stop the recording now. So